Hello and welcome to our project, which is feasibility of using a cloud chamber particle detector and a spatially varying magnetic field to ascertain the muon's magnetic moment. I'm Daniel BELZBERG. I'm a senior at PV High.
I'm Kapil Dheeriya, also a senior at PVI.
I'm John Kim, also a senior at PV High. So our project, as the name suggests, revolves around a lepton called the muon, which is essentially a more massive version of an electron. And due in part to its more massive nature, it has a high penetration power that could go through meters of rock residing on Earth's surface. And one of the elusive topics that have been vexing particle physicists for a while is the magnetic dipole moment of a muon. The value predicted by the Dirac equation shows some discrepancy compared to the value experimentally obtained. So in order to address this question for ourselves, we set out to do our experiment using a cloud chamber to track the trajectory of the muons.
Yeah, so the way we went about doing this was by first building a cloud chamber, which was built by cutting squares from a sheet of acrylic, putting them together, adding silicone to the joints to seal everything off. The chamber is then placed on top of a metal sheet, which is placed on top of some dry ice. Alcohol is held in an absorbent felt material at the top of the chamber, where this volume of alcohol mixed with the cold of the dry ice allows us to create a supersaturated environment of alcohol vapor within the chamber, which then, when particles pass through that vapor, they ionize the vapor, and then you can visualize the tracks of the muons. So by then applying a magnetic field external to the chamber, we can visualize how these trajectories are deflected and curved through the vapor, and we can then measure that. We can then derive the magnetic moment of the muon.
All right, so any muon passing through our chamber in the presence of that magnetic field generated by the solenoid primarily experiences two forces. The first force is the Lorentz force, force felt by any moving charge in the presence of magnetic field. And the second force is the magnetic dipole force, which is proportional to the magnetic moment of the particle and the gradient, or how the magnetic field varies. So what we did is we quantified how the magnetic field of our solenoid varied with space. And from that, we were able to derive and calculate the muon's magnetic moment by taking into account the net force, the centripetal force from the entire deflection, and the Lorentz force.
This led us to a final value that was on the order of magnitude of 10 to the minus 16, which is reasonably off from the value predicted by the Dirac equation of 10 to the minus 27. However, considering the restraints of our apparatus and the way our measurements were taken, we actually were very proud of this value, and we believe that it does well to prove our initial goal, which was proving that particle physics does not need to be the elusive field that it often seems it is. And as most particle physics is done in multi-million-dollar labs, we set out to prove that any high school students could engage in particle physics if they so chose to. And we hoped that this example would lead to more people joining the field in the future, so that one day the mystery of the anomalous magnetic moment of the muon could finally be solved. Thank you.